stop sharing, then you can,
Okay, should I share screen now?
yeah, you can do that.
Okay. So can you see the screen right now?
Yeah, I can.
Okay. So I'll
to-
probably not make it full screen because otherwise I won't see my mouse. So I'll just proceed this way. I don't know other ways for doing this, but I'll just do it.
It's okay.
Okay.
Just a comment. There are some settings in the in Keynote where you can say even in full screen you can still see your mouse.
Can you teach me? Is it teachable in real time? I don't know.
It's actually quite simple. I just looked up. You just go to Keynote and then settings. But it's not important. I don't want to keep you. Sorry.
Oh, okay. Maybe you can teach me later. Fine. So in future I know how to do this.
Okay, shall we start?
Yeah, please, Satoshi.
Okay, so it's great pleasure to have the Huajie Wan. He's going to tell us about the startup points at the holographic entanglement transition, enhanced corrections. Please.
Okay. Yeah. Thanks for the introduction and thanks for the invitation. It's very happy to speak at this wonderful virtual conference about our recent work on saddle points at holographic entanglement transitions. It's based on the recent work that I've done with the Xidong at the UC Santa Barbara. And so before beginning, maybe I should start with some explanation for the backgrounds and motivations for why we're interested in this particular problem. So let me just start by saying that one of the greatest breakthroughs possibly in high energy theory in the past 20 years is this notion of holography. And we know that one way to understand holography is that, well, first of all, it's identification, it's equivalence between two theories. One is a geometric or otherwise a quantum gravity theory in the bulk ADS space. The other one is a conformal field theory that lives on the boundary of an anti-de Sitter space. But one way to understand holography, or one perspective to view holography is to think of it as a sort of geometric manifestation of the sort of CFT ingredients in a one-dimensional higher bulk ADS space. And in particular, such a geometric manifestation usually takes form of a certain kind of saddle point objects in the calculations when we take the holographic limit, namely when we take the limit where the central charge or the gauge or the gauge Boole rank, if the CFT takes form of the gauge theory, goes to the infinite limit, and also while the coupling at the CFT goes to strong coupling, so that the bulk sort of has a Einstein gravity type of description. So in that particular limit, when we do certain calculations in the boundary CFTs, sometimes some saddle points objects arises from such calculations. And in many instances, such saddle points has a bulk geometric interpretation or bulk geometric meanings for it. So let me just give you the simplest such examples. I should say the simplest such example is, in other words, the simplest probe of the bulk geometry is the well-known RT formula, which allows us to compute the entanglement entropy at the boundary CFT. And in particular, it says this boundary calculation of entanglement entropy has in the holographic limit has a saddle point interpretation, and the saddle point, the result of this saddle point interpretation is the well-known RT formula, which says well, everybody knows that, which says the entanglement entropy of this particular bulk subsystem is equal to the bulk, boundary entanglement entropy is equal to the bulk minimal surface area, where the minimal surface sort of anchors on the boundary of this entangling region. This is the content of the RT formula, and as I shall review very shortly, this formula arises as some kind of a saddle point calculations from a boundary perspective. So let's just see how that appears. First, let's just very quickly recall what's the definition of the entanglement entropy. The entanglement entropy is defined with respect to a global state psi. And also when we specify a boundary subsystem A, then we can calculate the corresponding entanglement entropy. And the way to do that is to first define or first construct the reduced density matrix on this subsystem A by taking the trace over its complement. So we get a reduced density matrix, and then we take the trace log of this reduced density matrix. From that, we get the entanglement entropy, or otherwise known as the von Neumann entropy. However, if you look at this formula, you realize that to literally compute it, you need to know how to compute how to take the log of an infinite dimensional matrix, this reduced density matrix. And technically, that's a very formidable or difficult task. So what usually people do in terms of proceeding with this calculation is to go via this called the replica trick. So the entanglement entropy is usually computed by first computing a related entanglement quantity called the Rayleigh entropy. And the Rayleigh entropy is defined by this formula. In particular, it's given by well, first of all, the Rayleigh entropy is defined with respect to an integer n that we call the Rayleigh index. So for each integer n, we can calculate the corresponding Rayleigh entropy. It's given by this formula. Whereas Zn simply denotes the trace of this reduced density matrix raised to the power n. And Z1 is just the trace of the reduced density matrix itself. It's equal to 1 if you sort of normalize your reduced density matrix. So this quantity gives you the Rayleigh entropy. And you can actually check that if you take this quantity, you take the limit where n approaches 1. So first of all, this definition requires n to be an integer. But once you get the result, this will be a function that depends on this parameter n. So you can analytically continue this parameter to real numbers, and you can take this replica limit by n goes to 1, and then you can check that in the limit, you'll recover this definition of entanglement entropy. So this is what usually people do, or what usually how people proceed to compute this entanglement entropy, is via this Rayleigh entropy. And the reason this is helpful is that for this quantity, the trace occurs before the reduced density matrix raised to a certain power. So we can view this as some kind of modified partition functions, which we know how to calculate given a field theory, given a boundary conformal field theories. So the way to proceed that is that, so first of all, well, we can imagine our reduced density matrix can be represented by some kind of Euclidean path integral, where we have a physical branch cut left open that we define the reduced density matrix element. So this Euclidean path integral gives us the definition for the reduced density matrix. And so to compute this z to the n, or z sub n, we simply take n replica copies of this reduced density matrix, and we glue these branch cuts in a cyclic way. In that way, we obtain a closed manifold on which we can sort of compute the partition function on this complicated closed manifold. And this partition function will give us this quantity z sub n. And from that, we can, in principle, we can calculate the Rayleigh entropies. So this is just a general definition or general framework for how to proceed with this calculation. But in a particular context of ADS-CFT, we know that we can sort of take the holographic limit and use a saddle point approximation in the context of ADS-CFT. In particular, it means that this branch manifold that we just obtained by this cyclic gluing procedure defines a boundary manifold in which we want to calculate its partition function. And the usual language of ADS-CFT simply teaches us that if we want to calculate this quantity, what we need to do is to start from this boundary manifold, which is this branch manifold, and which defines a boundary condition for the bulk gravitational dynamics. And we fill the interior by solving the Einstein's equation. And we find a particular saddle point solution for the interior. In that way, we perform a saddle point calculation for this boundary partition function. And in particular, the saddle points approximation requires us that the interior solves the Einstein's equation. So in particular, the interior should be some kind of smooth bulk gravity solutions. If we can find such a bulk gravity solution, then we managed to find we managed to compute the partition function on this row to the n. And in other words, we know how to calculate this z sub n, and then we can take the replica limits and get the entanglement entropy. But this is general framework for how to view this calculation in ADS-CFT. So in terms of how to proceed, in other words, how to construct this bulk solution, part of the answer is provided by Xidong in 2016. One of the method, or one of the prescription to view the construction of the bulk solution is to use the so-called Cosby brane construction, which allows us to construct the quotient of the bulk geometry. And in this construction, the Rényi index n that I just mentioned, that defines the Rényi entropy, this Rényi index n, it enters in this construction simply as a parameter that specifies the brane tension for this Cosby brane. So the brane tension is given by n-1 divided by 4n times g Newton. So this gives the brane tension. So you insert a Cosby brane with this particular brane tension into the bulk geometry, let it backtrack, and then you obtain the quotient bulk geometry from that. So the advantage of this construction is that originally in the definition of the Rényi entropy, n can only be positive integers. But now in this quotient construction, n simply enters as a number that gives you the brane tension. So in this construction, you can continue n from integers to real numbers. And then, or we can take the replica limit that n approaches 1. So that's why we can make progress in ADS-CFT using this framework. And we notice that as n approaches 1, the replica limit, this brane tension approaches 0. So we can do a perturbative calculation from the original bulk geometry and extract the leading order in this n-1 sort of contribution to this quantity, this partition function.
Can I ask a question?
Yes.
If you want to analytically continue a function where you only know the integer value of it, yeah. Then you besides knowing that information, you also need to know the function at infinity. But this Cosby brane construction supposedly will give you that information. Is there a way to see what's that information on the CFT side?
You mean Carson's theorem?
Why do you expect that this particular NA continuation will give you the right answer?
I don't have an immediate answer for what that additional insight provide us into, but you are definitely correct that the boundary condition is a key ingredient for this replica trick to work. But at this point, I don't know. I don't have a concrete picture for what this brane construction provide us with about the boundary conditions at infinity. But you're absolutely right. This is a key ingredient for this formula to work. And in principle, one should check that it satisfies Carson's theorem to extract to make sure that this is a correct analytic continuation. But I don't have a concrete picture for this. Okay. So let me proceed and by saying that so in this prescription we can extract the leading order in n-1 contribution to this quantity. And you can this is a bulk calculation that perturbative bulk calculation. In principle, you can sort of track all the intermediate steps, and then in the end, you'll realize that the end result, this leading order contribution, gives you the RT formula. The entanglement entropy is given by the area of the minimal surface divided by 4 times g Newton. So this is a holographic motivation for the RT formula, and we see that the important intermediate in the intermediate step, an important ingredient of this calculation is this saddle point approximation, which allows us to construct the bulk solution explicitly and take the replica limit of the bulk solution and get the RT formula. So this is a connection between the RT formula and saddle point approximation, or saddle point objects. And we see that these saddle point objects give us the simplest geometric probe of the bulk geometry, which is the minimal surface area. Okay, so now let me proceed and by saying that we notice that in the above derivation there are two underlying assumptions. One of them is that we're assuming that in computing the bulk solutions, or in constructing the bulk solutions, only replica symmetric saddles are important. In particular, that means on the boundary, there's a replica symmetry that permutes the n copies of the boundaries of reduced density matrix. But whether the bulk solution satisfies this replica symmetry or not is a dynamical question that in principle, we don't know the answer. It could respect the replica symmetry, or it could spontaneously break the replica symmetry. We don't know, that's a dynamical question. But somehow in deriving this RT formula, we always assume that only the replica symmetric saddles are important. In other words, these replica non-symmetric saddles they never play important roles in the gravity dynamics. So this is one of the underlying assumptions. The other underlying assumption is that when we construct the saddle point geometries, we always assume that only one particular saddle point dominates the path integral. In other words, there could be others, in principle, there could be other saddle points, but there's always a hierarchy between these saddles, so that only one of them is a dominant. So from these two underlying assumptions, they lie the key sort of basis for the RT formula to work. So from this, it is natural to wondering, so what happens when, say, one of these assumptions or both these assumptions break down? Like what will happen? What will happen to the RT formula? Whether we should expect any modification to the RT formula, or there are new ingredients, new physics that comes into play. And one can imagine that one of the scenarios where this happens is when we have two competing saddle points where they have comparable contributions. So the contributions are comparable. We never have the case that one is dominant over the other. So in ADS-CFT, this scenario translated into the scenario when we have two different candidates for the bulk RT surface, and these two candidates, they have approximately the same area for the RT surface. Oh, sorry, the same area. So when this happens, we say that the RT surface goes through a phase transition, and so we're interested in the case where we're right at the phase transition and see what happens. And one of the prototypical cases where this kind of phase transition occurs, there are many different scenarios where this thing can happen. But one of them that we're going to look at in this talk is when we are interested in the entanglement entropy of a high energy eigenstate, and we want to calculate its subsystem entanglement entropy, and we want to vary the subsystems so that the subsystem is exactly equal to half of the total system size. When that happens, the entanglement entropy goes through a transition. And we notice that here, since we are talking about a high energy eigenstate, so in particular, the total state is a pure state. So we always have this symmetry that's, the entanglement entropy of a system is equal to the entanglement entropy of its complement. So this curve is always symmetric about half line. So that's why at the half point, we encounter a phase transition. So this is a transition we're going to look at, which sort of encodes information that we are interested in, when some of these assumptions for the RT formula breaks down. So this example that I just mentioned, if we viewed it in ADS-CFT, then it corresponds to a geometric transition in the preferred RT surface configuration when the background geometry is that of a black hole geometries. So for example, if you have a black hole microstate, so you have an effective sort of horizon that your RT surface needs to wrap up. So for a given subsystem, you have two choices of RT surface. One that wraps up the horizon this way, the other wraps up the horizon this way. So they are both allowed RT surface configurations. And we see that when the system size is equal to exactly half, these two RT surfaces has a symmetry that relates one with the other. So they have equal sort of areas. So this is a geometric sort of picture for why this transition is happening. So our goal is to look at this setup or this scenario and ask the following questions regarding the previous assumptions that lay the ground for the RT formula. One of them is that we want to ask, so how do the various saddle points participate at this transition? So we can imagine at this transition, there are various saddle points that comes into play. So how do they participate? And in particular, one can realize that this transition they characterize the switching of dominance between two replica symmetric saddle points. So these two RT surfaces, they come from when we uplift them to the corresponding range entropy calculation. They come from different replica symmetric bulk saddles, and they simply switch dominance at the transition. So yeah, is there a question?
I have a question here. So usually when we use I have a question. So
Yes.
I was alluded by the host. No? Can you hear me?
Yes, but not very clearly.
Usually when we use the RT formula, we ask the RT surfaces to be homotopy to the
Yes.
part A, but
Yes.
here I'm confused by the
Yes, I got your point. I got your point, Professor. So you're asking, usually when we talk about RT surface, we require the RT surface to be homologous to the boundary subsystem. But here, for example, if this is our subsystem, then this RT surface is certainly not homologous to it. The reason I'm including it is because, as I mentioned, I want to look at the scenario where I'm looking at the high energy eigenstate. So it's a pure state, it's an eigenstate. So translated into ADS-CFT, this corresponds to not the true black hole geometry, but more like a black hole microstate. So for a black hole microstate, it's a pure state. So the homologous condition should not stop us from considering this type of RT surface. So in other words, the horizon is not real in some sense for the microstate. It's only emergent notion when we sort of average over all the microstate. But for a particular microstate, the horizon, we don't completely understand what's the interior structure, but that's our expectation that the homologous condition shouldn't stop us from considering such configuration if we are only considering a microstate.
I see. Okay, thanks.
Yeah, thanks. Okay, so yeah. So a particular question that we are interested in is the effect of the replica non-symmetric saddle points. So as I mentioned, this transition corresponds to a switch of dominance between replica symmetric saddle points. But we can imagine that in principle, there could exist saddle points that don't respect the replica symmetries. And we want to understand whether they play any important role in this transition. And for this, to answer these questions sharply, we need to focus on a particular aspect of this transition. Something that's special, that is special about this transition, only happens at this transition. And then we can focus on that aspect and ask, how do these saddle points contribute to that particular aspect? And this particular aspect that we're interested in is the so-called enhanced corrections. So I'll explain more what do I mean by enhanced corrections later in the talk. Okay, yeah, so yeah, now let me specify what do I mean by enhanced corrections. So I should say that these enhanced corrections for the chaotic high energy eigenstate has already been shown for generic chaotic eigenstate ansatz. It's work done by Schwendike and his student in 2019. They proposed this particular ansatz for a chaotic eigenstate for the total system, where this EA and EA bar are the subsystem energy eigenstates, and this Cij are independent Gaussian random variables. And this ansatz was proposed based on the eigenstate thermalization hypothesis. You can actually check that if you look at a small subsystem of this total state density matrix, then the reduced density matrix looks like a thermal density matrix when you do the average over it. So this is a motivation. So they want to look at the entanglement entropy for this particular microstate as they vary the subsystem size. And they found that, so first of all, away from the transition due to ETH, the entanglement entropy is very well approximated by the corresponding thermal entropies. And also this thermal entropy, the thermality, the thermodynamic limit was controlled by some large parameter in the setting, In that setting, the large parameter is the volume of the system, which is a V. So usually you expect that if you calculate the exact answer and compare to this thermal approximation, the deviation should be at most order 1. However, they found that when you are right at this transition, and you compare the exact answer with the thermal approximation, you find that the deviation scales like square root of V. So this is a much enhanced correction compared to the usual order 1 correction that you see away from the transition. So this enhanced correction is what we will be focusing at this transition, because it only happens right at the transition. So what we're going to look at how to understand these enhanced corrections. So in particular, we would like to understand this in the context of ADS-CFT. In particular, we want to use RT formula to understand this enhanced corrections. And to proceed, we need to again use the replica trick. So we need to take a step back and revisit the range entropy calculations in the context of ADS-CFT. So this is a plan that we are going to take. So this is rough outline. I think I'm running slightly late, so I'll skip these formalities and just go right into it. So let's start with the, first of all, setting up the calculation for the range entropy when we are looking at the chaotic black hole microstate. It's a black hole microstate. So before doing this calculation, maybe the first thing that we want to do is to understand that, to clarify that in terms of the Euclidean path integral, how does the density matrix of a chaotic high-energy eigenstate differ from the density matrix of a true canonical ensemble? So this will provide the key ingredients for us to do the holographic calculation for microstate. So we know that the thermal density matrix, when the total system is given by a thermal density matrix, then it is this density matrix is characterized by a KMS condition along a thermal cycle. Okay. Along a thermal cycle. So the Euclidean path integral is given by that on the torus, on the surface of the torus, where the thermal cycle goes like this. And when we translate this Euclidean path integral into ADS-CFT, the bulk solution will fill this the interior of this torus, and this thermal cycle will become contractible in the bulk. So it becomes a black hole geometry. So this is a true canonical ensemble. But for a microstate, for the reduced density matrix of the microstate, the boundary Euclidean path integral looks almost identical to that of the canonical ensemble, except the boundary condition is different. So now the thermal cycle, see, this is the thermal cycle. The thermal cycle no longer closes on itself. The KMS condition is not exact. It doesn't close on itself. But instead, there are a pair of open cuts on this thermal cycle, where on these open cuts, we need to specify the microscopic information that are specific to this eigenstate. So for example, here, if I imagine sort of our eigenstate are some chaotic eigenstate characterized by some chaotic, some random coefficients that defines the eigenstate, then these random coefficients C are what we need to specify on these open cuts on this thermal circle. So this is the difference between the Euclidean path integral representation for a true microstate and a canonical ensemble, is that we need to specify additional information on these cuts on the thermal cycle. So given this, let's see, this key doesn't work. So let us proceed, and let us proceed with the range entropy calculation. So the first step is to obtain the reduced density matrix. So for that, we simply glue along the A complement and get this form of the reduced density matrix. So it has two pair of branch cuts. One is the branch cut that we specify the matrix elements. The other is the open cuts that we specify the state information. And now from this reduced density matrix, we want to calculate the range entropy. So, but what we are really interested in is calculate the disorder average of the range entropy. But we should distinguish between the average of the range entropy versus the range entropy of the average reduced density matrix. These two are completely different. This will simply give you the thermal answer by ETH. but this will contain information that are specific to the pure state. So we want to calculate this type of average. So let's see how to do that. So since our randomness is specified by this random parameter C, which are assumed to be independent Gaussian random variables, so averaging over them simply amounts to doing the weak contractions. So we simply take a pair of C and C star and replace it by the identity operator that glue the corresponding corresponding state. So in terms of these path integral, the weak contraction proceeds like this. So we take n copies of these reduced density matrix, and a weak contraction simply corresponds to gluing an upper boundary with a particular lower boundary. We simply glue them together so that these thermal cycles are again glued together. They are no longer open cuts on thermal cycles. So this is the effect of the weak contraction or the disorder average. And here I'm just showing the most obvious way for doing the weak contraction. We simply glue the adjacent upper and lower boundaries together. But for generic n, for n larger than 1, we can easily imagine there are other ways for doing the weak contractions. For example, this is another way for doing the weak contractions. It's we're no longer gluing the upper and lower boundaries. And for example, here we're gluing the lower boundary and upper boundary in cyclic way. This is also a valid weak contractions, and we should also include this in our disorder average. And so these different weak contractions give us different closed boundary manifolds that we need to fill the bulk with different bulk solutions. In other words, these different weak contractions, they give us different saddle points for computing this Schrödinger entropy, this average Schrödinger entropy. Let me comment that, so in principle, there are many ways for doing the weak contraction, but we can show that in the ADS-CFT limit, only the contraction of the planar type dominates in the holographic limit. So by planar type, I mean, for example, this type of weak contraction is planar, but this type of weak contraction is not planar. You can actually check that these type of contractions are always subdominant to these type of contractions. And secondly, we can always reorder the segments of the path integral so that the weak contraction takes the uniform form, that the weak contraction only connects the adjacent upper and lower boundaries. We can achieve this by sort of reordering the segments of the corresponding Euclidean path integrals. We call this the canonical representation of the branching structures. But we need to pay a price for doing this reorderings. The price we pay is that now the weak contraction, they all look the same, but then the branch cut structure will be different over A and A complement. So let's look at a particular example where we're taking the Rényi index to be n equals 3. So here for n equals 3, we have 5 different weak contractions. Here I'm just showing one of them. We see that this green arrows, they denote the gluing along the branch cut, and these red arrows, they denote the gluing on the open cuts that we specify the microstate informations. In other words, the ones we need to perform the weak contractions. And we see that this particular weak contraction is already in canonical representation because the weak contraction is already happening between adjacent upper and lower boundaries. So we don't need to do anything to that. But this guy is not in canonical representation because the weak contraction is not happening in the canonical form. So we need to sort of label the different segments of this path integral, and we need to reorder. We need to regroup these different segments. Here I'm just labeling them by these numbers so you can keep track of where they go. But you can see that by rearranging them, you can make this path integral into this form where the weak contraction happens in the canonical way. But the price we pay is that now the branch cut is no longer happening along A. Now it's happening along A complement. So in this sense, we obtain a canonical representation by switching the branch cut structure from A to its A complement. This is another example. And this is a third example where we see that the weak contraction happens this way. For this, again, we can follow the same trick by labeling these segments and do the reordering, play the reordering game. So now the weak contraction is in canonical form. But now the branch cut structure is more complicated. So for example, the branch cuts connects a complement among these two copies, and it connects A among these two copies. So it has a mixed branch cut structures. And we notice that this weak construction, it's always subdominant. It's never dominant in either sort of regime as we tune the subsystem size across the transition. And furthermore, it breaks the replica symmetry because the gluing doesn't respect replica symmetries. Let me comment that the different weak constructions give rise to different closed boundary manifold that we need to compute to get the average Renyi entropy. So our task in ADS-CFT is to fill these boundary manifolds with bulk solutions, and these bulk solutions will correspond to different bulk saddles for computing the Renyi entropies. So now let's see how to construct the bulk solutions and resum them, right? So we see that in canonical representation, we need to fill in the following. These are boundary manifolds. These are the weak constructions for disorder, and these are the branch cut structures. And since the weak construction only connects upper and lower sort of boundaries, we can, for each sheet of these branch manifold, we can sort of always imagine it to be some kind of segment of a black hole geometry, because this weak contraction is the one that's consistent with the KMS condition. So it looks like a thermal, it locally looks like a thermal state. So we can replace it by some kind of black hole geometries, and constructing the bulk solution simply amounts to gluing these different black hole geometries so that they satisfy Einstein's equation in our context. So let's look at the previous examples for n equals 3. So for this weak contraction, we can imagine sort of the particular branch structure simply says, this is the way we should construct the bulk solution. We simply glue the black holes, the segment of the black hole geometries that are along the A subsystem. We glue them together, and those along the A bar subsystem, it simply glue to itself and form a black hole geometry on itself. And this is the familiar bulk saddle that people use to compute the Renyi entropy for the mixed state for the black hole geometries. We are the well-known sort of bulk solutions. And this is the other. This is the weak contraction that gives you the other replica symmetric saddles. So here we need to glue, instead of gluing along A, we need to glue along the segment along a complement. And this is simply gives us the Renyi entropy bulk saddle that we use to calculate the thermal answer for the A complement. And for this weak contraction, the gluing structure is more complicated. So simply following the topology of the gluing, we know that we need to glue the black hole geometries in a way that looks like this. But this gluing procedure doesn't respect the replica symmetry. So in principle, as I said, so in principle, this gluing construction, it breaks the replica symmetry simply from the boundary condition point of view. And so in general, it is very difficult to construct such bulk geometries. But in our work, we're interested in the particular limit. We're interested in the limit where the black hole microstate has a very high temperature. So in this high temperature limit, we can neglect features that happens along the thermal cycles. And also we can neglect phenomena that are localized near the boundary of these entanglement cuts. So in this particular limit, we can see that in this limit, we can construct approximate bulk solutions simply by gluing segments of black hole geometries and subjected to particular matching conditions. So let me just show you the recipe for constructing a generic saddle point in this type of constructions. A generic saddle point is represented by m cycles along sort of A and m plus 1 minus m cycles along a complement. And we need to glue these different cycles together. And to construct the black hole geometries, we can sort of imagine that each of these m cycles are filled in by a particular black hole segment geometries with some temperature. And each of these m plus 1 minus m cycles, each cycle are also filled in with a particular segment of black hole geometry with another, possibly another temperature. So we have two different black hole geometries filling up different segments. And the boundary condition we need to impose is that the energies for these black hole segments, when we add them up, they need to equal to the microstate energy that we started with. So this is a matching condition. And in our limit, this matching condition is the only remaining sort of content of the Einstein's equation. So once we solve this matching condition, we solve the Einstein's equation in our limit of interest. So there's an equivalent way for constructing this generic saddles. So maybe I should speed up and maybe should skip some technical details, but you can actually show that an equivalent way to construct these solutions is to also take the quotient of such generic bulk saddles, and then for each quotient, we can obtain them by inserting what we call a double defect construction. So we simply insert two different type of brane defects or cosmic branes, one along A and one along A complement. And these two different type of defects, they have different brane tensions that depends on M, where M is the parameter that labels the particular bulk saddles, the bulk saddle topologies. So for each M, we have two type of defects and their brane tension are given by this. So we simply insert them into the original black hole geometries and let it backreact. And in the end, the backreacted geometry will be the quotients of this generic bulk saddles we want to construct. Okay, so this is a general prescription for doing that. These are some technical comments. Maybe I should skip. So now we know how to construct each individual saddle points in our limit of interest. So our task now is to resum these saddles. And then as a result, when we resum these saddles, they will give us an effective action for the cosmic branes. So we can simply do this resummations. So we resum these partition function for each saddles. Notice that for each M, we will have a degeneracy for different weak contraction. They give rise to the same topology. And this degeneracy we can calculate from some combinatoric analysis that are given by the so-called Nayarana number. There are some specific numbers that you can calculate by combinatorics. So now we have all the ingredients to do the resummations, because you see that each individual sort of effective action is given by the Nambu-Goto actions, where the brane, so this S brane is the Nambu-Goto action for the cosmic brane, and the T is the brane tension that depends on N. So now we can perform this sum over these these different saddle points. So we sum over the different topologies first, sum over M first. So we need to do this sum. This sum can be, so amazingly, this sum can be done explicitly. So it will give us some effective action for the cosmic brane configurations that we call S effective. So this is the effective action for the cosmic branes. And the effective action, the explicit form of the effective action looks like this. It takes form of some complicated hypergeometric functions in terms of Nambu-Goto cosmic brane sort of configurations. So let me say that we obtain this effective action by resum all the bulk saddles, including the replica non-symmetric ones. So we get the effective action. And as a result of the resummation, the effective action is non-local. It's a non-local effective action. Namely, the effective action doesn't take form of inserting a local source that we know how the source sort of backreact. Here, it's not a local form like that. But still, this effective action depends on N, sort of explicitly. So we can do the analytic continuation to a non-integer N and take the replica limit. So we want to solve the dynamics of this effective brane action, just like the way we solve the usual cosmic brane, so the effective action. And here, because of the particular limit of interest we're interested in, we can do this in a fixed error basis, which is a particular convenient basis in ADS-CFT that allow you to organize your path integral in some convenient way. And the advantage of doing that is that in our limit, in this fixed error basis, the path integral actually reduces to a one-dimensional ordinary integral that looks like this. So this E is this integration parameter E, they more or less resembles the the subsystem energy in the subsystem A. And these SA and SA bar, they are the subsystem density of states with the corresponding energy, subsystem energy here. I may need to go over slightly for maybe 5 minutes, if that's okay. Okay. So we call this exponent F1. So the resummation of the different brane topologies, different bulk topologies, allows us to get this one-dimensional integral, which we need to calculate. And hopefully, we can understand in the enhanced correction from this effective action that we get from resumming all the saddle point topologies. All right, so now let's look at the effective actions. So since the exponent f1 that I just circled, the f1 is proportional to in generic system, the F1, you can check the F1 is proportional to the system size V times the temperature times the central charge of the CFT. So it's proportional to these three parameters. So by taking any one of them to be large, we can use the sort of stationary point, so the method to approximate the integral that we just obtained. So here we choose to make V to be the large parameter, just to be consistent with the previous story. So for generic case, we can use the stationary point method to compute this effective action approximately. So if we have we have a particular stationary point E star, then this integral is simply approximated by the corresponding Gaussian integral around around this stationary point. This is just a simple usual story. But let's see what happens at the transition. At the transition, we have a symmetry that reflects across the subsystem equal to half of the total energy. So there's a reflection symmetry. As a result, this exponent has two symmetric stationary points. They give you the equal contribution to the integrals. So for generic Rayleigh index n, these two stationary points they're far away from each other. So the integrand has two well-separated stationary points, and we can approximate the integral by two independent Gaussian sort of integrals. So this full partition function is simply approximated by twice of the single Gaussian integrals, and this gives us a correction to from the microstate Rayleigh entropy to the thermal Rayleigh entropy that is order 1. It's proportional to log 2. It's order 1, but it's not enhanced. So why is it enhanced? The enhancement comes from when we take the replica limit, namely when we take the Rayleigh index n approaching 1. As we do this, the two stationary points, they collide. They become closer and closer to one another. And in this process, an effective flag direction emerges in between these stationary points. So the potential here sort of becomes approximately flat. And we can actually compute the width of this segment of these flat directions. And we found that this is proportional to n-1. So this is the width. It's simply the distance between the two stationary points as you move them, as n approaches 1. And we see that this flat segment, they results in an enhancement compared to the Gaussian approximation, because in the Gaussian integral, it's exponentially suppressed from one side. But here we have a flat segment. It's not suppressed. So as a result, it corresponds to an enhancement to the calculations. And you can actually extract the leading order in n-1, the leading order effect from this enhancement. And you will find that this enhancement actually give you the enhancement that is predicted by the previous general analysis. So this is enhanced correction that we have predicted from the general analysis. Here we use the saddle point calculation in ADS-CFT and reproduce this enhanced corrections. So technically we finished our task, but let me just conclude by some discussion and outlooks for what these tell us. What lesson can we draw from this particular case study, this particular calculations? First, let's go back to the original question. Namely, we asked, are the replica non-symmetric saddles, are they important at this transition? And the answer is definitely yes. Because we can imagine we're doing something else. Namely, we only include the replica symmetric saddles B1 and Bn, you know, the two replica symmetric saddles. So we include both. We only include these two of them, and we do the integral over the internal subsystem energy. So in principle, this ansatz it could dynamically produce both sides of the transition. So in one side of the transition is simply dynamically determine which term sort of dominates. However, this ansatz will completely miss the important phenomena of the enhanced correction. If you simply plug this ansatz in, you will never find the enhanced correction at the transition point. So this means the enhanced corrections doesn't come from, it's not enough to simply come from these replica symmetric saddles. The replica non-symmetric saddles play a very important role in generating these enhanced corrections at the transition. So okay, now so we know that they play important roles, but exactly what exactly do they do at the transition? For this, I should say that it was shown that one can get the enhanced correction if we simply impose by hand the following ansatz, namely for each of the internal energy, we simply pick out the we by hand pick out the minimal configuration for these two replica symmetric ones. If we use this ansatz, then we can get enhanced correction. Notice that this ansatz is different from this ansatz because this ansatz it involves a non-analytic function, which is this minimizing function. This is non-analytic. So this is different from this. So one way to understand the way that these replica non-symmetric saddles do is to say that they sort of dynamically implement this very bizarre ansatz for computing the effective action. Namely, you simply by hand pick out the minimal one. So, and including the replica non-symmetric saddles sort of dynamically implements this ansatz. Okay, so these are this concludes the technical discussion, and let me end with some questions for the futures. First of all, we see that by summing over these different topologies, we get this non-local effective actions. It will be interesting if we can understand more about the dynamics of such effective actions. For example, can we understand these non-local effective action as encoding some interactions between these brain defects? And for example, we see that the enhanced corrections comes from the flex segment that emerges in these effective actions. But from a dynamical point of view, can we understand this flex segment as some sort of exchanging soft modes between the original brain sort of defects? You know, they have some dynamics, and as we tune towards the transition, some mode becomes soft, and from exchanging soft mode, you know, they generate this enhanced corrections. Can we have some kind of pictures like that? This leads us to this more philosophical questions, namely, are the cosmic brains, are they more than just auxiliary tools? Originally, they were proposed simply to help you construct the bulk saddles, so they are completely auxiliary. But here, from these examples, it seems that they have their own sort of intrinsic dynamics. So can we understand, first of all, is it true? And if it's true, can we understand it more? For example, do they have intrinsic dynamics? Does the intrinsic dynamics include sort of non-perturbative effects, like instantons, for example? And also here, all the semi-classical pictures emerges because we're doing the average over the random variables. But if the system is self-averaging, then these non-perturbative effects should also exist in the individual realizations. Can we understand these non-perturbative effects without doing the average over the randomness? And last but not least, here we looked at one particular entanglement transitions, but there are many other well-known entanglement transitions. For example, the simplest one is when we have two intervals in ADS-CF T2, it will also go through a type of Hawking-Page-like transition as we tune the conformal ratio between the two intervals. So there, one can also ask whether this enhanced corrections happens there. That's another question. We believe it should be generic, but the analysis will be much more difficult than what we do here. So it will be interesting to perform these. Okay, so that's all I want to say. I'm sorry for going slightly over time, but thank you.
Okay, thank you very much. Questions?
Can I say is there a zero temperature limit?
Sorry?
There's zero temperature limit. It seems to me this kind of enhancement really relies on thermal background or a black hole.
Yes. This only happens when either the eigenstate has very high energy, so the so the corresponding effective temperature is very high. So it's a phenomenon related to ETH. However, for two interval case, we still believe that, here technically it relies on the setup being in a high temperature limit, but I should say that more underlying mechanism for this is the underlying chaotic nature of the high energy eigenstate. So for the two interval case, we believe that there also, it's a holographic state, right? And there, the correspondence of the analog of the chaotic Hamiltonian here is possibly some chaotic features in the entanglement structure of the two interval state. In other words, the modular Hamiltonian may have similar chaotic features. It's just harder to grasp these chaotic features, but we believe the underlying mechanism should also exist there in the two interval case.
Okay,
so if somehow,
yes,
by some other clever way for doing this calculation, we can get the enhanced correction, it will tell us something about the modular sort of spectrum of this two interval case.
So if I choose to think about a thermal field double for a given state, whatever it is, so can I see the mechanism from this purification after purification? Purified horizon.
Thermal field double.
So if you have a horizon, I can just purify. I can consider instead of one but two sides an eternal black hole.
I see. So so your pureness doesn't come from microstate, but comes from simply purify the thermal.
Yes,
system.
the black hole. Yes.
Let's see. I believe so. Maybe it will correspond to some kind of transition in the reflected entropy of the. The entanglement entropy in the thermal field double state, which is related to the reflected entropy of the original thermal state. So maybe it can be formulated as some kind of transitions for the reflected entropies. But we need to think about geometrically more carefully about what kind of transition can occur in the two-sided scenarios. But in principle, I believe similar stories may be there.
Okay, thank you.
Any other questions?
Can I ask a quick question? This enhanced deviation from the thermal state close to the transition, does it correspond to any particular measurements? Any set of operators that if I measure, I would be able to tell particularly that I'm deviated from the thermal state?
That's an interesting question. So, in principle, if you believe entanglement entropy is a measurement, it's not measurable in general, but entanglement entropy is something concrete that you can calculate and you can find its deviations. But I suspect if you simply plug in an ordinary observable that satisfies ETH, maybe similar things would happen there.
I see.
But at least special things should happen to the observer. But see, the entanglement entropy is the log of the partition function. So right. The log of the partition function. The log of the partition function has enhanced corrections is not necessarily related to the expectation value of a particular observable in the reduced density matrix having similar behavior. So I wouldn't say that exactly this type of enhanced corrections occur. It may take other forms that are specific to sort of simple observables, but I'm not sure exactly what this special phenomena may correspond to.
Right. In my mind, I was wondering whether, let's say, a local operators could detect it, yes. Whether it is necessarily some global thing that is detectable, such as by entanglement entropy.
Yes. But local entanglement entropy is a trace log
right.
of the reduced density matrix, whereas ordinary right. observables are O times the reduced density itself and taking trace. So definitely at the transition point, the entanglement structure is going through some kind of drastic transition between two different patterns. So the reduced density matrix has some, definitely it has some sort of,
right.
some special thing happens to the matrix, to the individual matrix elements. And these matrix elements, when we sort of take in the trace of log and we see its effects accumulate into this enhanced corrections.
Mm-hmm.
But whether, you know, the matrix element itself traced over some other observables, what their effect will be, I'm not sure. But that in principle there should be some right. You know, some deviation from the usual ETH expectation. But I'm just not sure what's the exact sort of expectation. How, you know, what's the exact expectation for the deviation?
Thank you. Thank you.
Okay, so it's time. So let's thank the speaker again.
Yeah, thank you.
So let's switch the speaker.
So should I let me stop sharing. All right.
Yang, can you make the Junbao as the co-host? Then so that he can share the screen.
Can you see my?
Yes, we can.
Okay.
Okay, so let's start the second talk in the afternoon session. So the second talk is given by Junbao Wu. He's going to tell us about loop operators in 3-dimension n=2 fishnet theories.
Okay, first I wanted to thank all of the organizers to invite me to attend this wonderful workshop and also give me this chance to introduce our recent work. So this talk is based on work done with Professor Ding Chen and Dr. Jia Tie. So this is a kind of continuation of my work on closed loop operators in 3-dimensional series. So in non-abelian gauge series, or in another word, in the MLS series, the definition of usual closed loops is like this. We know that they play very important roles in gauge series. For example, for special shape of water loops, the wave will tell us about the anti-quark potential. They give us the criteria for corner confinement. This is in fact the motivation for Burton to introduce these loop operators. The web of special Burton loops also has initiated to Westman function when carnival particles is accelerated. It was immediate energy. So, as you can imagine in supersymmetric gauge theory, the so-called BPS Wilson loops. The Wilson loops preserve some of the supersymmetries will play an important role. In fact, the first example of such BPS Wilson loops appeared after ADS-70 correspondence was proposed. So the definition of such a place was loops in equal to MS series, where you would not only gauge fields but also together in the joint representation of the gauge group. It plays a very important role in the study of ADS-70 correspondence. I would like to become a non-integer story short from the volume point of view. The web of the circular BPS was can be completed using supersymmetric localization. Such as we can compute the web not only in the weak cupping diameter and the strong cupping diameter, we can compute it for arbitrary to the cupping and for arbitrary rank of the digit. So I think this services it provide one of the earliest exact check of ADS-70 correspondence beyond the checking the symmetry and beyond checking the qualities protected by supersymmetry. It can also be studied using integrability. So it's better for custom work looks and Docker and Korea Marcel Sewer has important contributions. In this talk, I will focus on loop operators in three-dimensional case. The story about the BPS version loops in three-dimensional supersymmetry theory has more pieces and fun. So last year there is one wonderful comeback review by Docker and many other people. In three-dimensional angle to six consensus method series, so-called ABGM series, the 1/6 BPS was the first constructed by these three groups, including Professor Chen and myself. So this construction is based on previous construction by Gato and Yin in three-dimensional case with less social symmetry. So this construction is similar to four-dimensional case. So that was loop is personic. So it comes to gauge fields and standards. But in the gravity side is find that the simplest pure membrane of spin solution would in fact half BPS. But in the three-dimensional side at that time, we find in this construction we cannot find half BPS was loops due to such a membrane of harmonic spin solution. Then this becomes a puzzle. So is ADS-70 correspondence booking here? Luckily, such a puzzle was solved by Drucker and Takanini 1 year later. They constructed in a very beautiful way a half BPS version loops. In this construction, they find it's very important to couple to formulas in this theory as well. Several years later, with Oya and Zhang, we find that inside the ABGM theory, such a construction of Drucker and Takanini can be generalized to 1/6 BPS cases. So we found the formalic 1/6 BPS was loops. So the quantity of this formalic 1/6 BPS was loops was proposed only in last year. They suggested a special mixed boundary condition on the watershed of this fundamental stream solution. In this year, this Wilson loops is putting in the classification of superconformal down defects. So one under cooperative studied the classification of superconformal non defects, starting with supersymmetry and defect supersymmetry and representation. So define the 4-dimensional case and the 3-dimensional case has a very huge difference. So these formatic 160 BPS Wilson loops can be understood as a marginal deformation of half BPS formatic Wilson loops. I would like to say it under debated that whether such a formatic 160 BPS Wilson loops are truly BPS at the quantum level. The work of Korea and one give very strong support from specialist side and also the representation side. This formatic 160 BPS Wilson loops at BPS even at the quantum level. But we didn't have a proof in the previous series side. I think such a proof will be quite hard. One way to check this point is to compare the results for the web of Wilson loops, both from the perspective calculation and also from supersymmetric localization. Either with a part of from the very beginning of a 3-dimensional localization, one should choose a regularization scheme which is consistent with localization. For BPS Wilson loops, Thompson and his student point out this should be done at the family method. But in fact, the perspective calculation at the family method as a handful order for formatic Wilson loops are very complicated. On the other hand, the inequality of open string chain from Wilson loops in ABGM series is another interesting but unsolved problem. So we want to study these problems in a simple setup. So this is our main motivation for studying loop operators in 3-dimensional supersymmetric frictionless theory. In fact, the frictionless theory has its own origin from integrability in ADS-70 correspondence. So I would like to give a very short review about it. We know that both 4-dimensional equal-to-4 super-MS theory and ABGM theory are integrable in independent limits. From the field theory side, this can be understood as the anomalous dimension matrix is mapping to an integrable Hamiltonian on certain for both theories. From the geospatial point of view, this integrability can be seen from the one-sheet theory of geospace. And this theory, in fact, are two dimensional integrable field theory in the free limit. So from the both sides of ADS safety correspondence in the final limit, we find the hint of integrable structure. This integrable structure is also very powerful. It permits us to compute certain quantities even non-prospectively, even in a non-previous sector. Both four-dimensional equal four supergeometry theory and APGM theory has many supersystems. So it's an interesting question to ask whether we can obtain such a high-dimensional field theory with less supersymmetry, but still has such an integrable structure. There are several ways to find such examples. One way is to consider exactly marginal deformation of this theory. In fact, among such deformations, only a few will preserve the integrability in the final limit. Most well-studied cases are beta and gamma deformations. They are defined by certain star product. 5 years ago, product carbon students found that by taking spatial double staying limited fields are decoupled, and one will need to integrable series with only scanners and sometimes with also formats. The theory of technically is called the fissionette theory. So I just show you this diagram. So please look at the left diagrams. So these diagrams are contributed to a 10-point coordination functions, and at this look level, this is almost the only contribution diagrams. So this diagrams is like a fissionette, and all diagrams in this class are like a fissionette. So this is the reason why this series is called fissionette series. So now I would like to move a brief introduction to APGM theory, is gamma beta deformation and related fissionette theory. So APGM theory is a three-dimensional super-tensile theory with n equal to 6 super-conformal symmetry. So the gauge group is UN1 times UN2, and the tensile level K and M. The matter fields in this series, including 4 scanners and 4 formulas, is a bidimensional representation of this group. So this is the action of APGM theory. It includes the tensile part, the gauge1, the kinematic term for the scalars and the formulas, the scalar potential terms, and the cover depth terms. Starting with this theory, we will perform so-called gamma deformation. We just repeat all of the original products in the among fields in the Lagrange by the Fourier star product. The star product is defined first between this 3x3 anti-symmetric matrix. So these gamma 1 to gamma 3 are constants. It also uses three global charges. This small QA are global charges. So in this series, we have SU4 asymmetry. Then we can take the three Cardan subgroup, three Cardan U1s of this SU4 asymmetry. Then we can read off the three U1 charges of the using these U1 charges and this same matrix, we can define the star product and perform the gamma information. Then we will take the spatial double scaling limit. In fact, there are several ways to do this, but we take this one. So we just take gamma 1 and gamma 2 to be 0, and take gamma 3 to be purely imaginary and go to infinity. Then we take the copy to be 0, but with this combination fixed. So this is a spatial double scaling limit. This is not the simplest one, but this is the one page. So the idea of this series like this now is quite simple. The gauge field, the transverse gauge field has been decoupled. So this Lagrangian including the kinetic terms and also the scalar potentials and the Yukawa terms. Notice one of the important features of this series is that this series is not a unitary series. So we plan to construct the BPS loop operators in this series. We do this by using the very general prescription in one of my older work. So using this, we can construct the BPS timeless line operators in Minkowski space-time, or BPS line or loop operators in Euclidean space. So this is a construction, but I don't plan to go to the details. This is an example of BPS circular loop operators. So if B is the botanic part, so you can include in the scanners. And this F including the formulas, and in the construction we will use some spinors. So the spinor U plus mass is like this. So we find the two kinds of BPS loop operators. So we can show that the classically this loop operator is Q exact up to a constant. So if this relation is valid also at the quantum level, we will have a prediction for the wave of this circular loop operator. So its wave is a constant. So it has no quantum corrections. We want that to check this during perspective calculations. And one loop level, we have only one diagram. At two loop, we have this three. So the number of common diagrams is much smaller than the family computing. It became silly. During the computation, we realized some early regularization scheme should be improved. Let me introduce the details. In fact, the perspective computation of webs of Watson loops usually be performed during point solution regularization. The linked number of Watson loop control and the actual control is called family. This is a topological invariance. As I have already mentioned, to compare with the results from supersymmetric localization, the perspective calculation should be done as a family based one. But we realized this regularization scheme is wonderful for bosonic BPS Watson loops, but for the harmonic BPS Watson loops, the spinors in the definition of the Watson loops is not taken into account. What I mean is that this. So this U plus and U minus are in fact solutions to Keynesian equations. But the Keynesian equations depend on the control of the Watson loop. When we introduce some extra control, the Keynesian equation will be modified. So you should find a new solution to these new Keynesian equations, and including this solution as a part of the regularization scheme. Let's go to the details. So we will use the Hopf vibration to pattern this three-dimensional sphere and also three-dimensional Euclidean space. So we parameterize the standard S3 like this. Here, phi and eta parameters are two spheres, and for fixed phi and eta, the top cycle is the fiber. Then we use this standard projection to map this three sphere to the three-dimensional Euclidean space. This projection will give the following parameterization of a three-dimensional Euclidean space. You can see when you take eta equal to 5 to 0, the top cycle is the Watson loop control with the width. If we choose 5 to be 0 and the eta to be very small and only keep the terms up to the first order of eta, we will obtain this control. This control is already used in the perturbative calculation. Our new suggestion is to consider this GPS condition for the spinner's path manners. Notice the first equation is just a Kenyan spinner equation another control, but now we consider not the loop control, but the accessory control. The auxiliary control. So then we can find the solution up to the leading order of eta. So with the solution, our suggestion of the new regularization scheme is like this. For each such integral appears in the perturbative calculation of loop operators, we replace the control as before, but we also replace the spinner U. For example, for U pass, the result is like this. Of course, this new regularization scheme makes the computation much more complicated. But we thought this is the one more closer to the instrument to compare with the calculation. So using this new regularization scheme, we do the perturbative calculation up to 2 loop order. We found the numerical evidence that already above 1 loop and 2 loops diagrams give zero contributions. This is consistent with the prediction from the calculation. So this gives support that these loop operators are PPS even at the quantum level. In this work, we also studied the cusp operators. So cusp versus operators in this study is very important. They are linked to many other important quantities that impact the divergence of Coulomb amplitudes, anomalous dimension of twistor-2 operators. So in equal to 4 theory, the cusp anomalous dimension has been completed during integrability, and for some previous cases, it can also be completed during the calculation. But Barcena and Corbett suggested that such study in FGM case will give us the dispersion relation of the backgrounds on the FGM spin chain. These are conjecture for this dispersion relation was given by Gromov and Cedar. But nobody has completed the computation suggested by Marcel. Even the integrability of the open spin chain from was announced in FGM service not proved yet. So because of the time, I will omit the details. We constructed the cost non-operators in this picture next series. For this non-operators, the left ring or the right ring is half PPS, but the cost non-operator are non-PPS. We computed the value of these concepts now operators up to 2 loop order. The result is that I omitted the result. But using that, we can use the description paper to extract this generalize the potential. Notice that as a 2 loop order, besides the usual linear divergence, there are also quadratic divergence. This is different from the ABGM. After our paper was submitted to arXiv, we were informed that the prescription in this paper fails starting at the 3 loop order. So Bonini and Corbett started the cast the word loops in the net limit. So they find the beginning at the 3 loop order. There are some group vector structure which cannot appear in the right-hand side of this prescription. So even for ABGM case, a new prescription is needed. But till now, nobody knows this beyond the limit. If we accepted this prescription, we obtained this generalized potential. We need to do some renormalization. The natural renormalization condition is to demand that when phi equals to 0, the renormalized potential should be 0. From this condition, we obtained this renormalized potential. Then we can compute the universal cusp anomalous dimension. The result is there, but here we think that the most important problem is to find a new way to obtain this generalized potential. So this is the main result of our work. So let me conclude. So we started the PPS now and the loop operators in 3-dimensional equal to Frictionless series. So during our study, we suggested we found a new recognition scheme for PPS harmonic loop operators. We want to stress it's not only for the loop operators in Frictionless series. It should be also applied to PPS word loops in general specific vector series. So this should in some sense, the proper computation of harmonic BPS version loops perspectively is much more complicated. We also studied the classical non-operators and computed generalized classical anomalous dimension. To follow future work, I think one of the important problems is to find a new way to compute the web of the loop operator more efficiently. It's also very important to study the integrability of open spin chain from version loop operators in ABGM study. Maybe as a warm-up, we can further try to study the integrability of spin chain from non-operator in fictional series. In the four-dimensional case, the holographic deal of four-dimensional fictional series is studied by Gromov and Server. The result is quite different from the usual holographic duality. They call the new dual series Fishy chain. So I think it's interesting to study the holographic dual of three-dimensional Fishy series in terms of this Fishy chain, and also study the dual of the loop operators constructed here. So in three-dimensional cases, there are much more type of version loops than in the four-dimensional case. So we could study many kind of renormalization group for node, and also body node deformations among different version loops. Such a construction of fermionic BPS version loops can be also tried in high-dimensional cases, such as four-dimensional and five-dimensional. In this case, we should introduce some dimension for parameters in the construction, but I think nobody forbidden us to do this, and if we can construct this successfully, we can also consider how this fermionic version loops fit in the classification of one and his collaborators. This is all of my talk today, and thank you for attention. And finally, I would like to introduce to an important Chinese journal, so-called Science China A. This including physics, mechanics, and astronomy. You are welcome to submit your important work to this journal. Okay, so thank you for your attention.
Thank you very much. Questions?
Yes, I have a question.
Okay,
thanks for the nice talk. I wanted to know, normally in the fishnet theory, one of the advantages is that the types of Feynman diagrams is much more restricted, and often one can get all order calculations. I wanted to know if there's any chance of doing it in this, with these observables.
The answer to your question is that this, in fact, you can see first the number of diagrams is reduced hugely. For example, at the two-loop level, we only has these two diagrams. In the case for magic version loops, you have much more diagrams. And about all prediction, if you believe or accept that this Q exact this result is valid at quantum level, then the condition will predict that all of the quantum correction, all of the loop corrections are there. But I think it's not easy to prove this for all loops. At all loops level using perturbative calculation. I think here the computation is complicated than the computation for getting amplitudes or coordination functions in four-dimensional Fishernet theory. And also, I would like to mention that was almost only done for four-dimensional Fishernet theory. I think maybe almost no such computation at the three-dimensional case. I mean, for splitting amplitudes and also for coordination functions.
Okay, but if you are doing it just a two-loop order, that, I mean, that was done also for APJM or for other kinds of theories. So you're not really getting a simplification, a significant simplification from. So my question is, can you do the general gamma deformation rather than the limit, which gives you the fishnet theory, but any intermediate theory?
Okay. First, that is a given question we didn't consider yet. But for the Fishernet, the case, in fact, the computation is simple because the loop is much less. But that because their computation was done before, so we know the result is already there. But in fact, this computation is simple because the diagram is yes. But the key point we want to stress here is about the organization scheme. So we want to stress for non-unique case is not enough using Fleming minus one. You should use the U pass minus. That is the point we want to stress. The point is, yes.
Thank you.
Thank you for the question.
Any other questions? Okay, if not, let's thank the speaker.
Okay, thanks.
I think so. Today's session is over, and then we will meet tomorrow at 9 a.m. Is it the plan?
Yeah, I will just leave the room like for more
informal discussion.
More for 1 hour or something like that. If anybody want to discuss more about these two talks in the afternoon, you can do that.
Okay. Okay. So if somebody wants to discuss, just stay here and just you can discuss. And otherwise, we will meet at 9 a.m. tomorrow.